Yeah, I thank Ajit for inviting me and Ashish for, we had some discussion over the ASI and that's how I shaped this talk. So I'm here standing for UVIT, the Ultraviolet Imaging Telescope on board AstroSat. This is launched almost a year and a half from Sriharikota. So it's a multi-wavelength astronomy satellite. So it's having 4 X-ray payloads and 1 UV instrument. So I'll be talking about the UV instrument. So this is ultraviolet imaging telescope. So what you can see here. So it's a twin telescope. So one telescope for far UV alone and another one for the near UV and VIS channel. So its the diameter is 37.5 and field of view is 28.5 arc minute. And the important thing is that it can read at a frame rate of 29 frames per second as well as a window mode of 200 frames per second. And the spatial resolution is significantly better than any other previous missions like Galaxy. It's less than 1.5 arc second in near UV, nearby galaxies, star formation history of the universe, globular clusters, and planet and nebulae. So this is a schematic of the telescope in far UV optical design, and this is the near UV optical design. As I said before, the primary mirror diameter is something like 37.5 centimeter. And we have multiple filters, so one can do narrowband imaging, and in far UV and near UV, and in VIS channel. And the detector is a CMOS imager, and the interesting thing is that it detects the UV photons here in this side, and it gets converted to through photoelectrons here, and there's a set of photocathodes and multi-channel plates. So in the end, in here in the CMOS, we can detect the events. So it's the X and Y coordinates of the UV source in the sky plane. So this is how the image of Andromeda galaxy looks like with UVIT, taken with UVIT. This looks very nice. But in reality, astronomical source looks like here, because this is integrated over a time of one orbit, something like 15 minutes. So what you see here is a drifted event list. So it's basically X and Y positions across the 512 by 512 array, and this is a field of view of UVIT. So we need to do a lot of drift correction and other systematic biases to get rid of all these effects. And then the image looks like this. So this is a galaxy image. So what we record here is the event list in the detector. So it's centroid X and Y on time. So what you see here is the time in one column and X and Y position in the other column. And we can go to a time resolution of something like 34 millisecond in full frame mode. And if you can put a small window or the source, then you can read very fast, like 200 frames per second, which corresponds to 5 millisecond resolution. So this is how the image or centroid map over one orbit of observation looks like. So you can see the many sources in the field. So this is basically a 2D histogram of the field. So if I select a source here, I can basically get the light curve over there. So there's another dimension to this. This is a time dimension, time axis. So I get the plot of it's basically the light curve. So the time series analysis I can do on this. So I do all the statistical techniques of reducing the noise. I can even bring it down. So then I can start talking about time variability of the source. So this is how the source count looks like, and this is how the background looks like. So the interesting thing is that we are getting data over every orbit corresponds to something like 90 minutes. So we get something like 20 minutes per orbit. So we have many orbits in one observation. So the gaps you are seeing here is coming from we are missing data in that period, because effectively in one orbit we are getting only 15 or 20 minutes of data. So remaining data is lost, or we are not able to observe. So there are issues with the satellite because of that, because we can not continuously monitor a source. We will be getting gaps in the data, but we will be getting terabytes of data over the 1 year of mission life already. So the point is that if there is any transient, UV transient in the field of any observation, how to detect it. So one such science case which we did is that stellar flares from star-planet interaction. So the idea is that a planet hosting, a host star hosting a planet which is very close by, it's a hot Jupiter. So at a very close by separation, less than 0.1 AU, because of the magnetic flux tubes of the planet crossing the magnetic flux tubes of the star, stellar flares can happen. So whether we can detect that flares in UV. So that is a point which we look forward. And this is one observation which happened for that particular science case. So you can see this is a time series of the one observation, which is something like 60 kiloseconds. I'm just showing the snapshot of this. So how to detect a flare from this? Obviously, if there are many bright flares, we can detect, but if it's very faint or the flux change is very faint, how to within time to pick the strong flares? So that is one science case. So the real challenge which I want to pose is that we have enormous amount of even data lying there, but how to detect unknown transients in UV from the observed event list? That is a question which I want to ask, and that's a challenge, and I'm here to understand how to do statistical tools to extract that information. Thank you.
How many light curves do you?
Oh, we have something like 10, 15 sources observed, but that's the known sources.
The known sources.
Yeah, but there can be many which are not known, which are just flaring activity in the background. So these are like unknown transients, maybe.
Right. So, but you would have in tens of millions of total sources that have been observed.
Oh yeah, in that sense, there are millions of sources, yeah, which is already there over the last 1 year of observation, and which we'll be having in the future also, because the mission life is something like five years.
And right now, are those normally binned? You gave large frame rates, but how are they stored normally?
They are stored in 34 milliseconds.
Individual
bin. So how to bin it in time to extract the information there?
For these unknown transients that you are detecting, do you go back and look at the source again, or is just like
Yeah, that's the point.
observation?
So just to detect them and then go and characterize. So first we need to see whether there is a transient.
Whether it's a transient or not, yeah. But has that been done?
No. So the idea is that how to do that.
Okay. Because if it's only a single pointing observation and you detect a transient, then it could be a short variable, short period variable that is seen. But
so you're talking about the known source which is flaring up.
Yeah.
So in that time span, we may not be able to see the complete. But what I'm talking is that like some field, like M31 field, we have something like 60 kilosecond observation. So if there is a transient in that field. Time series, yeah. It's planned in the later mission time. Like now it's mostly proposal driven. So I think after 2 years of mission, there is last legacy surveys are planned.